All right, I'm recovering from a cold a little bit, so hopefully you guys can hear me okay. So I like to just start by kind of playing this video here to give you some perspective on the process if you haven't seen our website or maybe seen our TED Talk at some point in the past. But essentially what we've created is a new light-based approach to 3D printing we call digital light synthesis. And I wanted to take a little bit of time to give you guys an overview of what is involved in this technology, show you a few examples of how we're working with it in production, and of course answer any questions you have and open up the discussion. So I've been at Carbon for a couple of years. I lead our automotive business development now. Stepped into that role somewhat recently. I've bounced around between some different industries, but have been more automotive focused lately, so I may take a little bit of that direction in terms of my talk. But let me give you a little background on the company first before the technology. So we're based in Redwood City, just down the road here. We're about 220 employees now. We've raised a couple $100 million. You can see some of our investors here. Of course, Autodesk is one of them. In that second line of logos, those are all our early customers that actually turned around and wanted to invest venture capital into our company. A couple notable board members: Alan Mulally, former president of Boeing Commercial Airplanes, former CEO of Ford, obviously a huge asset to have on your board, crafting strategy of how to enter markets. Ellen Coleman recently joined our board, former CEO of DuPont, so she's really critical in our material supply chain strategy. We really see ourselves as much a materials company, and I'll go into that, as we are just a 3D printing company, so that's really crucial. In terms of the timeline, we started about four and a half years ago. We were in sort of stealth mode for the first couple years, and then we did that TED Talk, which I know got a lot of popularity about 2.5 years ago. Then about a year and a half ago, April 2016, we announced our first printer, all the way on the bottom left there, the M1 printer. And then in April of this year, we announced those other two products. The middle one's a smart part washer, we call it, essentially for automating some of the post-processing for cleaning parts. And the M2 printer, which is a step up in size from the M1. Fundamentally the same sort of hardware architecture. So Carbon was sort of started on the premise that this very big gap existed between traditional large volume manufacturing tools and where 3D printing was. And when we look at sort of traditional manufacturing, a lot of the plastics around us are made using injection molding. Injection molding is great at making things at really high volumes, but it's not great for the product development process. It's not great at making things at low volumes, especially at volumes of one, full customization. And so 3D printing has done a great job helping people make individual prototypes or customizing things. But we know that there are a lot of limitations to existing technologies. A lot of the heat-based technologies have sort of process limitations. A lot of the light-based technologies historically have had material limitations. And I think what we've essentially done here is solved those two main sets of limitations. With our process, digital light synthesis, and some of the formatting's gotten a little screwed up here. I converted it from Keynote to PowerPoint. But digital light synthesis is comprised of two major innovations. So there's a process innovation we call CLIP, continuous liquid interface production, which I'll show you right now. And then there's the materials innovation, which involves some proprietary sort of new chemistry approach that we call dual stage curing. So to start with CLIP, essentially what we're doing here is we are using a DLP-based UV light source. We're projecting patterned UV light up through a special window, more like a membrane, into a vat of resin. That architecture is not unique to us. There's probably a dozen printers out there that look like that. What's really unique to our printer is in this special window. So the window is transparent to UV light, but it's also permeable to oxygen. And we actually pull oxygen through the window while we're printing. And oxygen inhibits this UV polymerization reaction that we're actually using to define the shape of the part. So what we're doing is we're using oxygen right at the surface of the window to prevent the part from curing to the window, essentially to prevent it from sticking to the window. And that's been the biggest challenge with every other bottom-up light-based printing approach. Every time you expose a layer, you're essentially gluing that part to the window. You have to have some sort of mechanism for peeling it off, repositioning it. So essentially what you're looking at here is the oxygen is coming up through the window and creating this oxygen inhibition layer. It's a little hard to see. What we've done here is essentially taken a continuous CT scan of the cross-section of a print. And we pigmented the resin to show how it's flowing. And by maintaining that liquid layer But at all times between where the part is printing and the window itself, we're able to start accessing speeds and sort of the continuity of printing that wouldn't be possible otherwise. All right. So not only can we start printing at speeds that are a lot faster, we can also start printing completely homogeneous parts. When you break open our parts, cut open our parts, there's no internal structure, just like an injection molded or a machine part should be. Essentially because we're not now printing in discrete layers. We're actually printing in this kind of oxygen gradient, where from no cure to full cure. And so what we're seeing from that is fully isotropic properties. It doesn't really matter anymore how we orient our prints in terms of how they're going to behave. We're taking full advantage of all the material properties on all axes. And this, I think, has been a sort of fundamental advantage over a lot of these existing technologies. Now you can run accurate, FEA models on these parts. Now it's a lot easier to validate these parts during the design process. Any questions on the process itself, maybe, before I move into the materials? Yeah. Okay, the question was, have we thought about ultrasonic tools to help the process? I don't think so. We are playing with, I'm not going to go back to the slide, but if you think about that process of resin flowing in through this very narrow area, that's our rate limiting step, right? It's the time that it takes for that very viscous resin to flow in from the outside to the inside of the part to replenish it as we're pulling it up. And so we started to think about how can we print faster using heat, using positive pressure to reduce the suction forces, essentially, to make that resin flow faster. Yep.
Just a quick one. Can you elaborate on the oxygen gradient, the no cure to full cure comment you made?
Sure. So essentially, the resins that we use are reactive to UV light. When you hit them with UV light, they polymerize, they solidify. If there's a high density of oxygen, that reaction is inhibited. So we're using that to our advantage to stop the part from curing right at the surface of the window. As the oxygen moves through the window, it dissipates into the liquid, so that once you're about 50, 100 microns away from the window, you're getting full cure. But in the area between that, you're getting this gradient of curing. So you're never just curing one layer distinct from the next. There are these kind of polymer chains that are hanging down that are kind of getting engulfed in the next layer. So on the material side, what we've done is essentially integrate two different types of chemistries. One's UV reactive. That's the same sort of chemistry that we've been seeing for decades in SLA and polyjet. And then we've combined it with a thermally reactive chemistry, the same sort of chemistries you see being used in reaction injection molding, compression molding, other thermoset, heat-based manufacturing processes. And what it has allowed us to achieve is the benefits of processing material with light, right? The complexity of design and fabrication that you get, but with the properties of these thermosets, heat-reactive thermosets, which are much far superior to what you could get from SLA before. So when we look at our resins that we have available today, you'll see that a lot of these are similar to heat-reactive thermosets that are used today. Different types of urethanes and epoxies. We've essentially just figured out how to print these for the first time. Here's kind of a little glimpse of some of the direction we're moving into with future materials. We're seeing a lot of demand for clear materials, for much softer elastomers, much more sort of industrial grade, like automotive specific materials, aerospace specific materials, to meet all of those specific requirements you get for different industries and different applications. So we're investing really heavily in developing materials that are, we hope, going to be really production ready. Any questions on the material stuff? Yeah?
Do you think that eventually you could get a material so that you could print like a mold for like a part?
Like an injection mold?
Yeah.
Yeah, so the question was, are we developing materials for injection molding, essentially? We have a material cyanide ester that you can see up there, which is probably just about the highest temperature polymer that you can print today. It's about a 230 degrees C heat deflection temperature. I was having a discussion with a gentleman earlier about this, and it's just very hard to print that material in really thick sections. Our process does not lend itself well to big, thick, blocky things. that look like they were kind of designed to be machined. If we, to think back to that kind of flow, that becomes really hard and really slow and actually generates a lot of heat when we do that. So the short answer is yes, we can kind of do it with small molding tools, but it doesn't scale very well. So, yeah, question?
Question about the optically transparent material. Are we able to print different densities throughout the material so that you can actually, have optical applications for it?
That's a good question. I've gotten that before, and I haven't gotten a great answer from our materials team. I mean, the first goal is just to release a material that is pretty optically transparent, that could kind of help people develop like polycarbonate type parts. Long term, there probably are some things we can do with like different wavelengths of light, with different sort of cure patterns where we could maybe change the like diffraction index of certain sections and create some cool optical applications for sure. Yeah.
So all these names are too technical. So like for common people who want to use your printer in the future, like how would you explain these materials?
Sure. So yes.
How do you compare them?
Yeah. So to give you kind of some analogs, maybe from the thermoplastic world, our elastomeric polyurethane is very similar to like a TPU. It's like a rubber, right? It's a tough elastomer. Our flexible polyurethane we actually developed to try to meet a lot of the polypropylene specs. So very good for things like with clips and living hinges. It's highly elastic, but it's still a rigid plastic. Rigid polyurethane, I know this is overused by the 3D printing world, but it is actually pretty similar in ABS, pretty similar to ABS in properties. The epoxy, similar to like a low glass-filled nylon or PBT or something like that. The cyanate ester may be a slightly higher glass-filled engineering grade polymer. Does that help? So let me talk to you guys kind of briefly here just about a few different projects we're working on. One is with BMW, one of our investors and one of our earliest customers. And I think this is probably going to be the first time that we have a customer-facing 3D printed part in a commercial vehicle. And this will be, what you can kind of see here is what they call the side scuttle. It's like a name badge that goes on the outside of the Mini Cooper. Mini Cooper is owned by BMW. And this is going to be one of a few different design elements, customized design elements. This is the only one we can share right now, that is essentially made possible by our new technology. And so there'll be some add-on option when someone goes to buy a 2019 Mini Cooper where they'll be able to choose, what's the name on this? What is the pattern? What's the texture? For the side scuttle and a few different elements. So we're pretty excited about this. I think it's the first time that we've kind of proven that this material can withstand applications on the interior and exterior of a car. Of course, a whole lot of different technical requirements in terms of UV exposure, thermal cycling, compatibility with salt and chemicals off the road, and et cetera. One thing we're really investing in experimenting with different customers is what we can enable with new sort of digital texturing. I think you look at almost any product out there today, especially the surfaces inside your car, and they have some sort of texture on them, right? For aesthetic value, sometimes for like tactile sort of experience. It feels good. It doesn't feel cheap. Doesn't look cheap. And so that's been done by injection molding for a long time, and it's kind of a pain to do with injection molding. It's like the last thing you do before you actually go into production. So you don't really know you don't really have it at the prototyping stage. So that's one clear advantage. But I think the biggest value is what sort of textures can you create that were not possible before? And so this is just an example of one sort of clearly unmoldable texture, with these sort of undercuts. And this is printed with our elastomeric material. And I actually have a sample if someone wants to see it afterwards. But we're talking to automotive companies and other types of product companies about what if you put this on some sort of product that you're holding for a long time, or maybe holding in the heat, and it could allow sort of air to flow underneath your hand. Or if the steering wheel was really hot one day when you jumped in the car, right? It wouldn't be really uncomfortable. So we're playing with these sort of textures, with other textures, and we're really finding already that there's so much interest in what you can do with these in terms of tactile experiences, in terms of aerodynamics, in terms of fluid dynamics, in terms of sound absorption, and it's kind of just completely new areas that haven't been explored before because there was just no way to make these things. So the last thing I'll wrap up with is this project that we're working with Adidas on. I'm not sure if anyone's heard of it. But essentially, we're taking the first mass-produced sneaker to mass market very, very soon. I think towards the end of the year, there'll be a big announcement of when these shoes will be commercially available. But essentially, as you see on the slide, it's going to be hundreds of thousands of units next year. It's going to be millions of units in 2019. And so, of course, we've proven that this technology can scale. It can move very fast, and it can hit economic targets. I'm wearing a pair of the shoes right here. You guys are welcome to come check them out after. They're actually super comfortable. One advantage of this type of structure that, of course, you can't mold is that it breathes, right? So now air can flow through the midsole, whereas with the foam it can't. But I think the most impressive thing is that now with these types of highly optimized structures, engineers can take full advantage of sort of the behavior of structures and materials. Whereas before, typically you'd find some sort of density foam and you'd mold that to some sort of surface shape. Now you can actually tune each element. And the vision, eventually, that Adidas has is being able to customize a shoe for not just the exact topology of your foot, but the way that you run too. Do you land on your toe? Do you land on your heel? Are you a marathon runner? Are you a sprinter? Being able to completely customize this mesh to optimize whatever you are trying to do, whatever your body's trying to do. And so I'll just finish with a video that Adidas put together kind of on this collaboration.
When we first started with the idea of Futurecraft, it was to sort of guide us, to set us on a path.
It's a mindset and it's a philosophy to try things.
We're always bringing in new influences, new ideas, new collaborations. 3D printing, for example, was one of these new technologies that really had unlimited possibilities. The initial problem was, okay, can we actually make a running shoe out of 3D printed material that really works and works well?
So when we started thinking about doing 3D printing, we wanted to use liquids because liquids give you the most flexibility in material design. I think of light as a chisel. Light triggers the solidification of the liquid, but oxygen inhibits it. That allows us to have the object grow.
What's really interesting about this collaboration with carbon is we're seeing a convergence of a completely new manufacturing technology.
We're going to scale it with the best industrial partner in the business.
We're able to deliver tens of thousands and move into hundreds of thousands and into the tens of millions. That's clear in front of us.
We have this amazing opportunity to innovate the printing process, the liquid rising.
And growing in that context can give you new design thoughts you've never had before and new performance capabilities that wouldn't be possible by traditional manufacturing.
This three-dimensional mesh structure, it's a lattice, it's a matrix, it's a web of individual elements. Each one of those little elements is tuned specifically for a purpose.
These lattice structures behave quite differently than anything we've dealt with before. They're much different than foams. Now we have every individual area of the shoe to work with, which is a completely new horizon for us and a new venture.
If you really want to make a shoe that's a size 9, that same shoe for someone who's 180 pounds versus 100 pounds has got to be different.
We can go in within every single cell and engineer that exact cell to do exactly what the consumer needs it to do just for them.
That's fascinating. That's going to change how we create products and certainly how consumers experience products. And I think that's how we see something like Futurecraft 4D playing into the life of an athlete. I would say this is just the very beginning, and it sounds silly and cliche, but who knows, man? I don't know what's next, and that's what's great about going to work every day.